Hello, welcome to Basics of Finite Element Analysis. Today is the second day of our lecture for the in this particular fourth week, and in the last class we were discussing weighted residual method, and we had developed an expression for weighted residual method, which was this, where it is integral of the weight function psi I times residue. When you integrate it over the domain, it could be dx dy, that is 0. And then I had mentioned that based on this particular weighted residual method, it has different flavors, and depending on the choice of our weight function, it is a particular type of weighted residual method. So today we will discuss some of these methods, and the first method we are going to talk about is called Petrovgalerkin method. Petrovgalerkin method. Okay. So in this, the only restriction on the choice of weight function. So this is my weight function psi I, and so this is the weight function, and then my u is represented as phi j times C j. This is my primary variable. So in Petrov-Galerkin method, there is only one restriction on the choice of psi, and that restriction is that psi I should not be equal to phi. Okay, should not be equal to phi I. So it should not. So what that means is that these psi's is represented by an independent set of functions, and there is no restriction in terms whether it has to meet the boundary conditions or not. Okay. So you may want to pick a function which meets the boundary condition, that is fine, or if it does not meet, that is fine also, but it should not be from this set of phis. So that is the Petrov-Galerkin method. Okay. Now suppose our residue was expressed as, I am integrating it over the domain psi I. So C j A of phi I dx dy, and this equals some forcing function. So I am integrating it times psi I times some function of x minus a times phi naught dx dy. Now even if a is linear operator, even if a is linear, suppose I assume that a is linear, it need not be, but even if a is linear, this term is not symmetric. Okay. So when I construct my matrix, I will get some A matrix times some constants, unknown constant C will equal some forcing vector F. This will not be a symmetric matrix. So, in Petrovgalerkin method, the A matrix need not necessarily be symmetric. Okay. If we want this matrix to be symmetric, and if we see that A is an operator which is of even order, second order, fourth order, then we can weaken the differentiability and then get a symmetric matrix. But if we keep it as is, then A matrix will not be symmetric. So, this is all about Petrov-Galerkin method. The next method is Galerkin method. Okay. So, in Petrov-Galerkin method, we had this restriction that psi I should not be equal to, the weight function should not be equal to the approximation for the function for the primary variable. Here we say that psi I should be equal to phi I. Should be equal to phi I. So, the good thing about this is that we do not have to guess a new set of functions. If we have figured out some functions which are phi I, which we meet all the natural boundary conditions and primary essential boundary conditions, we can use same functions for weight functions. Okay. Here also A matrix need not be symmetric, actually is not need not be, it is not. It is not symmetric. And if we want to make it symmetric, again we have to see if A is a second order or a fourth order differential operator, then we can weaken the differentiability and then get symmetric matrix. But so that is the case. For linear systems, this Galerkin method and Rayleigh-Ritz method both of them give the same answer. Okay. They give the same answer. So, we have looked at, first one was Petrov-Galerkin, second one was Galerkin. The third method is called method of least squares. So, what do we do here? We ensure that the square of residue, when you integrate it over the domain, the square of residue when you integrate it over the domain is minimum. This is what we ensure. So, we will discuss this in detail. So, this is, so my residue is a function of x, y and Cj, right, and this residue is integrated over the domain, and if this thing, if this integral is minimum, for anything to be minimum, what does that mean? That its differential, in this case it will be, so what is the unknown in this? Cj. So, its differentials with respect to this unknown Cj, they should be 0. Okay. Actually, I will not write it Cj here, I will say Ci, because I will differentiate it with all if there are n unknowns values of Cj's, I will differentiate with every single Cj. Okay. So, I is equal to 1 to n. I is equal to 1 to n. So, what that means is 2r times again I am sorry zero. Okay. What that means is, look at this term in green. I can call this psi I. Okay. So, in method of least squares, the choice of psi I is partial of this R, which is residue with respect to Ci. It is partial of R with respect to Ci, and I can write this as del over del Ci. And residue was what? Some operator. Operator depends on the nature of the differential equation. So, some operator A, which was a function of x, y and u, right. So, x, y I do not have to worry. So, this is a function of sums of Cj phi j plus phi naught. This is my definition of u. This is un, right, and then there is also some forcing term minus f. Okay. So, this entire thing is my residue, and I am integrating this entire residue on the domain. Okay. Now, I say that if A is linear operator, then what will be the powers of Cj's? They will not be 2, 3, 4, right. The power of Cj will be only 1 if it is a linear operator, then because if it is a linear operator, what does that mean? That u will not come as square or cubic terms in the equation. It will only come in when its power is 1. If its power is 1, then the power of Cj will also be never be more than 1. It will always be identically 1. So, if A is linear operator, then if A is linear operator, then psi I equals, I have to differentiate this entire thing with respect to Ci, right. So, then psi I equals this thing and Cj phi j plus phi naught minus f. So, del over del Cj, right, and then again I differentiate it del over del, oh I am messing it up, Ci minus del over del Ci f. So, if it is a linear operator, first thing I can do is I can separate it in Cj and phi j, if it is a linear operator. That is what we had defined several lectures back. Now, this part, it does not depend on C at all, right, it only depends on phi naught. So, this is 0, this is also 0. So, the only thing which depends on C's is this thing, right. So, the next thing you should look is that in this term it will be basically del over del Ci A of let us say C1 phi1 plus C2 phi2 and so on and so forth, right. It will go on till Cn phi n. Okay. Now, when I differentiate, so what does that mean? That if I equals 1, then only C1 term will appear in the system, because the partial of C2 with respect to C1 is 0, right. So, partial of Cj with respect to partial of Ci is equal to this Kronecker delta Ij, and its value is 1 when I equals j, its value is 0 when I does not equal j. Okay, understood? So, because of this, what you will get is, if I am differentiating it with respect to the ith constant, all other terms will vanish and the only term which will remain will be A of phi I. Understood? Because of this, psi I equals A of phi I. Understood? Because all other terms will be 0 and the coefficient of phi I in this case will become 1, because partial of Ci with respect to Ci is 1 if I and j same. Okay. So, this is the second, this is the third method, which is known as method of least squares. Okay. Also, when you look at this, because I have this, what I am doing is, what am I doing? I am minimizing the integral of r square. So, this is mathematically it looks very similar to our first situation where we were minimizing I, which was a bilinear functional, bilinear and symmetric functional. Same thing is true here also, this is r square. Okay. So, this functional also looks mathematically similar to the I functional which we had discussed in context of Rayleigh-Ritz method. So, because of that reason, here A matrix will be symmetric. So, in method of least squares, your A matrix is going to be symmetric. And the last method we will discuss is the called collocation method. Okay. So, in this method what we say is that the value of residual n, I will make it discrete points. So, we identify in the domain, and at those n number of points, suppose I have an n term solution, so I need n equations. So, I identify n points in the domain which I think are important, and at those n points I ensure that the condition that this residual is 0, I enforce that condition. Okay. So, what does that mean? So, in this case my psi I is what? It is a Dirac delta function. It is a Dirac delta function. And its value is equal to 0 at all points except at location x I. So, it is not x to the power of I, it is just way to designate it, okay. And its value is 1 at x is equal to x I. So, in this case my equation is integral over omega psi I. This was my weighted residual statement, and suppose it was only one dimensional. So, d omega, right, and this I replace psi I by what? Direct delta function. Okay. And if you go back and check your mathematics, this is nothing but integral of, the value of this integral is equal to residue at location x I, and of course, it is a function of C j. So, this is equal to 0, because whenever you multiply a direct delta function by some function and integrate it, the integral of that entity is nothing but the function evaluated at that particular point. Okay. So, this is the condition for collocation method. So, in this case my psi is a direct delta function. In case of method of least squares, my psi was del r over del c, but effectively what we had seen that it comes down to a of phi I. In case of Galerkin method, psi I was same as phi I, and in case of Petrovgalerkin method, psi I and phi I, they were different, they were required to be different. So, that concludes our lecture for today. We will continue our we will start a new topic starting tomorrow. Thank you.